Hello and very welcome to this first video concerning MBR, Membrane Bioreactors for wastewater treatment. In this video I will go through the system layout and some key parameters in order to understand when to select an MBR as your treatment system as opposed or as an alternative to conventional activated sludge system. So let's have a look at the agenda for this video. First, we start out with the definitions, of course, followed by the types of membrane used in the MBR. Then I'll make a comparison between the conventional activated sludge system and the MBR. Then we come to the point MBR and subpoints process parameters and cleaning of membranes. This section is very important because here you will really see what differs an MBR system from the conventional activated sludge system in regard to the overall functions. Finally, in this video one, we'll have a look at when to select an MBR as an alternative to conventional activated sludge plant. With this, I welcome you to look at this first video. So let's start. Important definitions when it comes to membrane bioreactors, that is what we're going to have a look at now. First, we have the term permeate. That is the treated sewage water that has passed through the membrane and has been filtrated. Then we have excess sludge, which is the same as, of course, as in conventional activated sludge system. The bacteria is growing, so you need to remove the excess sludge in the process. Flows and flux. When you discuss membranes, you use the word flux to talk about quote-unquote the flow. And the flux is basically the volume over surface area and time. In this case, I have used liter per square meters and hours. Then we come to the driving force, the pressure drop over the membrane system. And for MBRs, this is referred to as the transmembrane pressure, the TMP. And this you need to remember, this abbreviation TMP, because this you will hear a lot when you start discussing MBRs. But the transmembrane pressure, the driving force to make the filtration happen, the pressure, in this case I've used Pascal as the unit. Then we come to the permeability. Basically, the permeability is the ratio of the flux divided by the transmembrane pressure, the TMP. And this is a parameter you will see when you are operating an MBR plant in the SCADA system. This is a parameter you will use to control and to see how the filtration and how the system is working. So permeability, very important to know what it means and how it is calculated from the flux and transmembrane pressure. With that, we'll move on to look at the different type of membranes we're using in wastewater treatment and the MBR systems. In the MBR, the only type of membrane we use is an ultrafiltration membrane, a type of ultrafiltration membrane. And if we have a look at this picture here, you will see that the ultrafiltration membrane is much more efficient than, say, sand filtration or rapid sand filtration. That means that the ultrafiltration membrane will remove all the particulate material and also bacteria and viruses, depending on how tight the ultrafiltration membrane is. That may vary, but all particulate material and basically bacteria will be removed by the ultrafiltration membrane. Now, just some notes in regard to the ultrafiltration membrane and dissolved substances. Here in the picture I just want to point out that the ultrafiltration membrane does not reduce dissolved nutrients, nitrogen or phosphorus compounds. So if you have a good flocculation in the treatment plant, the phosphorus will end up in the particulate material and will be removed. But if you don't flocculate or precipitate the phosphorus and it's still dissolved in the plant, it will pass through the ultrafiltration membrane. Now, in drinking water, you use other two types of membrane. That is the nanofiltration membrane and the RO, reverse osmosis membrane. And of course, these two types of membrane reduces also very small molecules and salts. But for the ultrafiltration membranes, it will only reduce particulate material and also, as I mentioned, bacteria. It will not remove dissolved substances such as nitrogen or phosphorus compound. This is very important to remember when we now go on to look at the system. The MBR has an ultrafilter, and the ultrafilter will greatly enhance the removal of particulate material in regard to the conventional activated sludge system. So let's have a look over the two systems compared on this picture. Here on top you see the conventional activated sludge system with the biological treatment, followed by the secondary clarifier. And in many plants, after the secondary clarifier, the water is discharged to the recipient. But in this case, I have added a rapid sand filter labeled 2 here, and also a third step, disinfection, which I've represented by a UV treatment labeled number 3. And the rapid sand filter will of course enhance the removal of particulate material greatly after the secondary clarifier, and with the disinfection unit we will also remove bacteria. So in this case we can assume that we have stringent discharge demand on the recipient. Let's look at the MBR system. Here below you see the biological treatment, which of course is the same for the two systems. Then you have the MBR unit with the ultrafilter. And the MBR unit can be said to replace the work of the secondary clarifier, the rapid sand filtration and the disinfection unit. So maybe a little bit jokingly you can say that MBR will be an all-inclusive when it comes to stringent discharge demand to the recipient. So you already see now where we are going with the MBR and what is required when you should consider using the MBR. But we'll get to that. Now let's have a look at what you can expect in regards to, for example, suspended solids concentration after the two systems. We will now get some figures in regard to suspended solids and bacteria comparing the two systems MBR and conventional activated sludge. So let's have a look at an overview picture of this. The effluent water quality in regard to suspended solids. Now, with a conventional activated sludge plant, using a rapid sand filtration after the secondary clarifier, you will reach about 3 to 5 milligrams per liter of suspended solids, which is quite in the low range. However, with an MBR system, the particulate material, the suspended solids, will be removed. So basically you will not be able to measure suspended solids in the water, but you will have to look at turbidity in the water instead. But the turbidity will, as a rule, be below 1 NTU, so it will be a very clear water. Then we will have a short look at bacteria, or more correctly the EU directive, which I've noted down here, in regard to the conventional and the MBR system. With a conventional system, including the rapid sand filter, the bacteria criteria is not applicable. You need the disinfection step after a conventional activated sludge plant. So rapid sand filter will not do the job for the conventional system. With the MBR, as I said before, all-inclusive, will fulfill the bacteria requirement as in regard to the bathing water directive. Then we come to the sludge concentration. Now, typically with nitrogen removal, we are probably running sludge concentrations about 3, 5, 6,000 milligrams per liter in the conventional system. Now, with the MBR, because the ultrafilter will contain or hold back all particulate material, we can run up to 30,000 milligrams per liter or 30 grams per liter of sludge concentration or total suspended solids concentration. So here we see the big difference between the two systems. And of course, bad sludge will not be a problem with the MBR because it will hold back all the particulate material. So with this, we're going to have a look at some operating parameters in regard to pretreatment, for example, but we'll get to that after this. Before we go over to key operating parameters, I just want to show you some notes on the two systems now when we've gone through the basic differences between them. So let's have a look at the picture. On the left-hand side, you have Membrane Bioreactor, some points, and on the right-hand side column, you have some notes in regard to the conventional activated sludge system. Looking at the Membrane Bioreactor, a correct pretreatment is crucial, and this is of course because the ultrafiltration membranes will hold back all particulate material. So it's very important to remove material that can mechanically damage the membranes or foul them. Also, with the MBR, you will have to take care of the fouling of the membranes during operation, which also means cleaning of the membranes. And of course, membranes is what really differs the two systems apart. Also, you have a decreased oxygen transfer, which you have to consider when you're looking at the MBR. When you're running at very high suspended solids concentration, over 10, maybe up to 30 grams per liter, 40 grams per liter, the oxygen transfer will decrease. So you will need more energy to put in the same amount of oxygen to the bacteria. This will of course cost more money. Finally, as we've seen, with the all-inclusive for the MBR, it will be less space demanding for the same equivalent effluent quality as for the conventional activated sludge. For the CAS system, there will be limitations in the TSS concentration compared to the MBR. Bulking and settlability of the sludge can be a problem with the CAS, which you won't find in the MBR. And finally, again, larger space needed if you have very stringent effluent conditions. With this note, I will show you some pictures in regard to the importance of the correct pretreatment before we then go into the key operating parameters. But now let's have a look at some horrifying pictures. Now we're going to look at the scary pictures. Here you can see 3 pictures, and first is the step screen, which is kind of clogged. The middle picture is actual damage to membranes due to hair and fibrous material, and the picture to the right is from a membrane bioreactor compartment. This just shows you how important it is to have the correct pretreatment, and I will come back to this in video 3 when I go through the practical experience from 3 plants. And I will also show you what to do in order to avoid this in operation. With this said, we're now going over to the key operating parameters for the MBR treatment system. Key operating parameters, that is what we're going to look at now, and they are the following: water temperature, process parameters, and cleaning of membranes. The key operating parameters, and we will now start with looking at the water temperature and the effects of that. The water temperature is directly correlated to the viscosity of a fluid, in this case water. Let's have a look at this picture. Here you see that the viscosity of water at 20 degrees centigrade is 1 times 10 to the minus third power. Compare this now with olive oil at 20 degrees centigrade. The viscosity of olive oil is 81 times 10 to the minus third power. And as you know, olive oil is much thicker than water. And the viscosity will vary with temperature. That you can see to the left here in the graph. On the graph here you have the temperature on the x-axis. On the y-axis you have the viscosity of water. And if you look at the graph, you can see at lower temperature you have a higher viscosity, a more thicker water, but the warmer the water gets, the lower the viscosity gets. This, of course, has an impact on the membrane filtration, the variations of the viscosity with the water temperature. So now we are going to look at the transmembrane pressure, which is directly correlated to the water temperature and the variations in viscosity. To show you how the water temperature and the viscosity affects the operation of the MBR, we're now going to look at some real figures from a plant in Germany called Nordkanal. And I will show you two graphs where we have measured in the one graph the permeability, which is the flux divided by the operating pressure, the transmembrane pressure, and a second graph with the temperature variations over the period when the permeability was measured, of course. So let's have a look at the two graphs right now. On the top graph you have the permeability on the y-axis. On the graph below, on the y-axis, you have the water temperature. And as you can see here, when the water temperature is high, the permeability is accordingly high. Because you have a lower viscosity, it's more easy to get the water through the membranes. And vice versa, when you have lower water temperature, the permeability will accordingly drop. Now, this is critical to remember when you design a plant, that the viscosity and water temperature will mean that it will be more easy or more difficult to put the water through the membrane. So, importantly, never forget to design for the lowest water temperature. With that, we'll go on to the next slide and see what we find. Now we have looked at the impact of the wastewater temperature variations over the year. What other effects might these temperature variations have? That we're going to answer with this slide right now. When you have a decreasing water temperature, that means that you need to increase the driving pressure in order to keep the same flow, to keep a constant flow. An increased driving pressure adds to the fouling of the membranes. That in turn brings us to a key point when it comes to membrane filtration, cleaning of the membrane. Increased fouling yields more frequent cleaning of the membranes. This we will talk about in a very short while. But before we do that, I'm just gonna touch on the SRT, the sludge retention time, and that effect on the fouling properties of the MBR unit. That we'll do now, and then we'll discuss in detail cleaning procedures. With the MBR, we're gonna have very high sludge concentration, or may have very high sludge concentration. So the sludge retention time is of course of importance. And I'm just gonna show you some literature data in regards to the retention times and fouling properties of membranes in MBRs. So let's have a look at the picture here. On the x-axis, you have the sludge retention time in days, and on the y-axis you have quote-unquote fouling tendency. You see a number of literature references, not quite up to date, but they give you an indication of that at some point you have an SRT that will give you less fouling. I'm showing this to you now just to wake the question. And always remember, variations in organic loadings will have an effect on the fouling of membranes and thus have an effect on the cleaning of the membranes. So when you start working with design or looking into the MBR, keep this in mind and look at the SRT and maybe go into the literature and check for more updated references. With that, we're going to go over and look at the cleaning. Now we're going to look at maybe the most important part of running the MBR system, how to keep the membranes from fouling. Let's have a look at some points. The main cleaning of the membrane is the so-called mechanical cleaning, where you have a coarse bubble system that constantly or intermittently aerates over the membrane surface to keep the sludge from clogging the membranes. Then you have a resting phase of the membranes. Basically, you shut on and off during operation. And here is a very important thing to remember, that during the resting phase, no filtration is done. So when you design or work with the membrane system, you need to take into account the downtime during normal operation for the membranes. Then you have a backflush system, which is mainly for hollow fiber. Then you have chemical cleaning in place. And this is basically using chemical agents to clean the surface of the membrane. Also, you have chemical cleaning outside the system. This is also for mainly for hollow fiber. This is the main points of cleaning. When we look at video 3, I will go through this in detail in regards to every plant on how they are operating their cleaning. But more and more in detail on this when we have video 3 and the practical cases. So with that, we're gonna go over and see what chemical cleaning means and what agents are involved. Independent if you work with wastewater and the MBRs, or if you're working with drinking water, when you clean membranes chemically, you need to have an acid and an alkaline cleaning. Let's have a look at this picture for the MBR system and the chemical cleaning. The alkaline cleaning is done with hypochlorite, sodium hydroxide, and the pH will be elevated, that is 9 to 10.5. Then acid cleaning, normally done with citric acid or hydrogen chloride, and of course a low pH around 2. Depending on the plant operation and experience, the chemical agents, pH and time for these cleanings will of course vary. But more about that when we go through the 3 case studies and video 3. With this, we'll now go and see when an MBR can be an option to a conventional activated sludge system. Now we have gone through the details of the MBR, how it works in operations. Also, we have made a comparison with the conventional activated sludge system. So if you keep that in mind, we're going to look at some points in regard to when the MBR can be an alternative to the conventional activated sludge system. When the recipient is a sensitive raw water source for drinking water production, basically when you have stringent discharge demand in regard to turbidity. When the recipient is used for bathing and recreation, that is when you need a removal of bacteria. Limited area of extension of an old wastewater treatment plant. Here you use the compactness of the MBR if you have stringent discharge demand that will force you to have the sand filtration, maybe disinfection step after the secondary clarifier. And finally, reuse of treated wastewater as a raw water for drinking water production. This is something that during the last year has become more and more important. So when there is an acute shortage of groundwater or surface water over the year, then reuse of wastewater is a possibility, and there the MBR is a strong card, so to speak. With this, video 1 is concluded, and I hope you enjoyed it and you've taken some points from it. Now in 1 or 2 weeks I will post video 2, where I'll show you a little bit about the different types of ultrafiltration membranes that is used. And then in 3 or 4 weeks time I will post video 3 with the practical case studies in regard to what we just talked about, but from plants that's been in operation for over 10 years. With that, I hope to see you again for the second video, or if you want to check out some other videos on my YouTube channel here. Take care, see you soon, bye bye.